Welcome to the Perceptive Engineering Operator Training Platform online tutorial. This video contains a demonstration of our Operator Training Platform, or OTP, for a fully simulated evaporator and multi-stage spray dryer designed for the production of milk powder. It has been designed to help process unit operators understand the process behavior and gain familiarity with the SCADA displays in a safe, offline environment. The OTP has been built around empirical process models that capture the input-output relationships for both the evaporator and spray dryer. The operator can interact with the training platform to make set point changes at any time and observe what would happen on the process plant. PID loops can be switched between manual and auto. Optimization scenarios can be quickly investigated, showing how changes to the process operating point will impact upon drying rate, powder moisture, and specific energy consumption. Alternatively, the operator can monitor a real plant scenario, take action as required, and compare the performance to what actually happened. OTP models are simply used to generate process responses and represent all the input-output relationships that have been modeled on the process plant in question. PID loops are also simulated so the behavior of the PID loops can be monitored. Operator actions can be made during the simulation to move the process to new operating states, such as those with higher throughputs or lower solids, for example. The OTP also offers the ability to set predetermined profiles for a specific process event, such as a tank-to-tank batch change. An APC scheme is also included as part of the OTP, which can be switched on and off and have the constraints limits modified. This feature helps operators learn the new modes of operation and eases the transition from entering set points to entering constraints. The OTP runs 30 times faster than real time. The two main elements of this particular OTP are the evaporator model, which predicts process responses to changes in the feed rate, the steam pressure, and the density of the feed, and the spray dryer model, which predicts dryer responses to changes in the evaporator product density, the inlet air absolute humidity, the inlet air temperature, the internal and external fluid bed temperature set points, and the homogenizer pump speed. Moving on to the OTP interface, it is mainly based around a menu bar found at the top of the screen. This menu bar provides an overview of the current simulation status and 12 buttons that open task-specific windows. I will now go through each of these buttons in turn, giving a brief overview of the functionality they provide. The evaporator overview provides a simulated evaporator SCADA screen with 3 live PID faceplates. This is a simplified version of the actual SCADA commonly found in a control room. In this case, the density controller drives the set point for the steam pressure, and the pressure controller itself must be in auto with an external set point to allow this density loop to function. Similarly, the spray dryer overview window provides a simulated spray dryer SCADA screen, this time with 6 live PID faceplates. Should you wish to use your own SCADA displays and PID faceplates for either of these windows, this can be accommodated to represent your own production facility. Next are the PID loop overviews. These provide a summary of all the configured PID faceplates and a live trend for each set of PID signals. In this case, there is one window for the evaporator PID loops and one window for the spray dryer PID loops. The APC, or Advanced Process Control window, provides a simulated SCADA display for operating the APC functionality. This shows the low and high limits, PVs, SPs, and other parameters associated with all the outputs or controlled variables and inputs or manipulated variables. At the top right-hand corner of the screen, there's also a box to select and deselect the APC to switch it on and off. When APC is active, it will drive the set points for the evaporator feed rate, the steam pressure, the inlet air temperature, the IFB, and the 3 EFB temperatures. It will also drive the HPP. The simulation will switch the density, level, and dryer exhaust air temperature loops into manual when the APC is active, and the set point values of these loops will track the values set by the APC. The objective of the APC is to maximize powder moisture and drying rate. The APC also has to keep the MVs and other CVs within the limits set on the screen. These can all be changed, and therefore the extent to which APC can increase moisture and drying rate depends largely on the limit values. To switch the APC off, simply press the Select/Deselect button. The Request and Confirm cells will turn red and the APC status will switch to Ready. The simulation will automatically switch the density, dryer feed tank level and exhaust air temperature loops back to auto when APC is switched off. The optimization window, which only applies while APC is active, shows the constraints for each of the MVs and CVs associated with the controller model, along with the calculated optimal operating point for each of these variables against their current actual value. This gives an indication of where the APC model will drive the process. The sticky curve window shows a Mollier diagram with the temperature and humidity condition of the ambient air, the dryer inlet air, and the dryer exhaust air. Superimposed on the diagram is the product's sticky curve. This combined visualization shows immediately how close the product is to being sticky. The reinitialize window is where the user can restart the simulation and change the initial conditions. The initial conditions can either be user-defined or predefined product-specific values. The initial conditions for both the evaporator and the spray dryer can be set separately. The values in grey are the default values for the selected products. If you've chosen to initialize the product from these defaults, then the values in grey will be automatically copied over to the text boxes when the blue button is pressed. The Trends window contains predefined sets of process variable trends. These are accessed through the pull-down menu in the top right-hand corner. The Dashboard window displays performance of key variables versus baseline, including process variability and energy consumption. The Scenario Player allows you to change the operating ranges of selected variables and shows where the resultant optimum operating point would be. This is completely independent of the APC optimization and can be used regardless of the APC status and whether the PID loops are in auto or manual. Finally, we have the Trainers panel. This is a configuration panel where disturbances can be introduced into the process, historical events can be replayed, and test assessments managed. Within the Event Mode section, there are two options, Steps and Profiles. Event Mode Steps allows you to make step changes to the finished product tank solids. When the tank solids are changed, a tank change with a small water flush is simulated. Event Mode Profiles provide you with a simple and effective way of simulating a realistic process event. Profiles are predetermined disturbances, but with the flexibility of allowing you to change the severity of the event, i.e. either low, medium, or high. You can also pause or reset profile disturbances. The OTP contains 8 test assessments that can be accessed via the Trainers panel. In this case, we're going to run test assessment number 1. To begin, press the Start Test button at the top corner of the Trainers panel window. After a few seconds, the process will reinitialize and the Trainers panel window will update to display a condensed mimic of the evaporator and dryer with key PID loops shown. In this test, the density, level and exhaust temperature PID loops will be placed into manual. The goal is to increase the density by 4 kg per meter cubed while maintaining a steady evaporator level. With each passing second, the test score reduces until the test objective is met. Also, the larger the deviation from the target, the quicker the test score falls. At the right of the window is a dial showing the overall score, based upon all tests carried out, and the test scores for each individual test. At the top of the window are a series of buttons to control the tests, a display showing the current test, progress and the status of the simulator, and finally a brief description of the test. Make sure you take your time to read the description before starting the test. In order to observe our actions and the process's response, it's worth opening the test's respective trend window. To do this, click on the Trends button and in this case select Test Part 1 from the pull-down. Zooming in on a smaller time range can make fast process changes easier to observe. Clicking on the Continue button starts the test and its countdown timer. The first move I'm going to make to increase the density is to change the steam pressure set point from 4.3 to 5 bar. Returning to the trend window, we can see the increase in the density target shown in red, but once the steam pressure increase takes effect, we can show this causes a large overshoot in the actual density value. To counteract this, I'm going to reduce the steam pressure to 4.7 bar. Returning to the trend, we can see that this has helped, but the outlet density is still above target. Finally, I'm going to increase the feed rate set point from 13 to 14 meters cubed per hour. Now on the trend, we can see that the density is finally reaching its target value. When the test is complete, the trainee score is logged and the trainer's panel steps forward in readiness to start the next test. Tests can be carried out in any order and also skipped over if required. A certificate can also be printed at any time. When the trainee is finished with the tests, press the Stop Test button and quit the trainer's panel window. That concludes this short introduction to the operator training platform. Should you wish to find out more information, please visit us at www.perceptiveapc.com or follow us on Twitter @PerceptiveAPC.